Hi all, welcome to SG Know How channel. We are back again with another exciting chapter in our series From Pixels to Prediction, where we unravel the mysteries of computer vision and the crucial role convolutional neural networks play in making sense of visual data. In our previous video, we explored the fundamentals of computer vision and introduced the significance of CNNs in image processing tasks. In this video, our focus sharpens as we dive into the heart of CNNs, the convolution operation. Before looking into convolutional operation, let us see the structure of convolutional neural network. Convolutional neural network, in short CNN, consists of an input layer, convolution layer plus activation function followed by pooling layer, which is then followed by fully connected layer where an activation function is used, and then finally the output layer. So for example, if the input image is a diseased leaf image which is given to the input layer, which is then passed on to the convolution layer where an activation function is used. The role of this layer is to use filters to detect the spatial hierarchies of feature maps. The output of this layer is a feature map which is given to the pooling layer. The function of the pooling layer is to reduce the spatial dimensions of feature maps, retaining important information. So after dimensionality reduction, the feature map is given to the fully connected layer where an activation function is used, and here it combines high level features for final predictions. The final output layer classifies the leaf input image as diseased or healthy leaf. The concept of convolution involves examining the transformation of one function when it interacts with another, resulting in a newly modified function. In the context of signals, this process is termed as one-dimensional convolution or 1D convolution, while for images it is referred to as two-dimensional convolution or 2D convolution, and for videos it is designated as 3D convolution. Mathematically, this could be represented as g of x comma y is equal to k convoluted with I of x comma y. Here, the asterisk symbol represents convolution operation. K is a kernel or filter, while I of x comma y is the input image and g of x comma y is the convoluted output. Filters are learnable weights that represent features like edges, textures, or shapes. So the values of the filters will be useful for extracting the edges, textures, or shapes. Another parameter that has to be considered here is stride and padding. Stride defines the step size when sliding the filter over the input, while padding is introduced to preserve the spatial dimensions, preventing information loss at the borders. So let us see the convolution operation with an example. As we saw, the convolution operation is mathematically represented as g of x comma y is equal to k convoluted with I of x comma y. Here we have a kernel of size 3 cross 3 and an image of size 7 cross 7. When the kernel is operated on the image, the pixel which coincides with the center of the kernel gets modified. The value is computed by element wise multiplication of the kernel with the pixels in the image. As shown in the image here, the kernel covers only the size 3 cross 3. To cover the entire image, the kernel has to be moved one position or two positions sidewise, and this is called as the stride. The convoluted output that we have got for this example for the first position is minus 1 multiplied with 3 plus 0 multiplied with 2 plus 1 multiplied with 1 plus minus 2 multiplied with 1 plus 0 multiplied with 2 plus 2 multiplied with 0 plus minus 1 multiplied with 2 plus 0 multiplied with 1 plus 1 multiplied with 3, resulting in a value of minus 3, which is replaced in the center of the kernel size, that is in this position of minus 3. As I said, the convolution operation is done by sliding the kernel either one or two positions or three positions in the sideways. So here, continuing in the same way, we have shifted the kernel one position towards the right. Now the 0 pixel, which is shaded in green color, will have a modified value, convoluted value by element wise multiplication. The value will be equal to 1 and it is shown in the figure convoluted output. The drawback of this is by applying the convolutional filter every time the original image sinks. That is, the output image has smaller dimension than the original input image, which may lead to information loss. And also, pixels at the corner of the image used in only one of the outputs than pixels in the middle, which lead to huge information loss. As we saw, the convolution operation has two drawbacks. The first one is the size of the convoluted output is not the same as the original image. And also, the pixels in the corner are not involved in convolution and hence information is lost. To overcome this, convolution operation with padding is done. Why padding is done and what padding is? Let us see with an example. So, to include the first pixel, the center of the kernel should coincide with the first pixel of the image, which is a corner pixel. So, if it coincides, then we see that there are no pixels for the first row and the first column of the kernel. So, we have to make zeros in those positions for the image, and this is done by zero padding. So when the image is padded with one row and one column of zeros on all the sides, we see that we get a zero padded input image with pixels on zeros on all the sides. So now the size of the image becomes 9 cross 9. So the original size of the input image was 7 cross 7, and after zero padding it becomes 9 cross 9. So we have seen how to overcome the drawbacks of normal convolution, and that could be done with zero padding. If we have 7 cross 7 input matrix, after zero padding it will become 9 cross 9 matrix. Applying convolution of 3 cross 3 on it will result in a 7 cross 7 matrix, which is the original shape of the image. In general, to know the size of the convoluted output with padding, let us consider an input size of n cross n and the padding length be p and the filter size be k cross k. Then the size of the output image will be n plus 2p minus k plus 1 cross n plus 2p minus k plus 1. So we have seen that zero padding can be done to get back a convoluted output with size similar to the size of the original image. This could be explained with one example. As we had an original image of size 7 cross 7 and after zero padding it became 9 cross 9, and now when a convolution is done on the padded image, we can see the center pixel of the kernel coincides with the corner or pixel of the original image. So the convolution results in a value of 6. That is, element-wise multiplication of the kernel pixels with the image pixels results in a value of 6. And then moving the kernel one pixel towards the right will give the next value. In a similar way, the entire image value could be convoluted and the size of the convoluted output is same as the original size, which is 7 cross 7. We have seen what padding is and why it is done. And there are two common choices for padding. One is called valid padding, another one is called same padding. Invalid padding, it means there is no padding is done. If we are using valid padding, the output will be n minus k plus 1 cross n minus k plus 1, where the size of the input image is n cross n and the size of the kernel is k cross k. While in same padding, it means here we apply padding so that the output size is the same as the input size. That is, n plus 2p minus k plus 1 should be equal to n. So here it results in a padding of k minus 1 by 2, where k is the kernel size, p is the length of the padding, and n is the size of the input image. Now, while performing convolution, we saw that the output convoluted image can be obtained by moving the kernel either 1 pixel or 2 pixels or 3 pixels to scan the entire image. So let's see what stride is. In the context of CNNs, a stride is the number of pixels the convolutional filter moves across the input data at each step during the convolution operation. Smaller strides result in larger output volumes, and this is mainly used for fine-grained feature extraction. This preserves more spatial information, while larger strides lead to smaller output volumes. This is used when spatial resolution can be sacrificed for computational efficiency. This reduces the size of the output feature maps. A stride greater than 1 is known as strided convolution. Otherwise, it is just called normal convolution. It reduces the spatial dimensions of the output value. When the stride is more than 2, we can see that the number of pixels in the convoluted output will be less, and hence it reduces the spatial dimensions of the output volume. Choosing an appropriate stride involves a trade-off between computational complexity and the retention of spatial information. The choice of stride depends on the specific requirements of the task and the desired characteristics of the learned features. We know how to compute the size of the convoluted image. But when striding is greater than 1, then to calculate the number of pixels in the output image or to calculate the size of the convoluted output, let's consider the following. Consider an image of size n cross n image to be convoluted with a filter of size k cross k. Assume a padding border of p pixels and a stride of s. The dimensions of the output image is given by n plus 2p minus k divided by s plus 1 cross n plus 2p minus k divided by s plus 1. For example, when n is equal to 7, p is equal to 1, k is equal to 3 and s is equal to 1. In the case of our example, which we have seen already, the output of the strided convolution will take a size of 7 cross 7. As we conclude our journey through the convolution operation in CNNs, let's recap our key insights. First, we saw what CNN architecture is. We explored the intricate structure, laying the foundation for robust image processing. Next, we saw about convolution operation. We unveiled the essence of CNNs where kernels transform input pixels into meaningful features with examples. We also saw about what padding is and stride is. We explored their roles in preserving spatial information and fine-tuning computational efficiency with an example. We saw what is valid and what is same padding. The choice of padding. Distinguished between valid no padding and same preserving input size for optimal outcomes. Stride in CNNs. So here we examined how varying stride impacts output volume, balancing complexity and spatial information. Our pixels have undergone a transformative journey, paving the way for accurate predictions. In the next episode, we will delve deeper into activation functions and pooling layer. Thank you for joining From Pixels to Prediction. Here are some references. Thank you.